All right, so next up, we're going to look at the formation of a non-ideal solution. So as we said previously, most of the time we don't have an ideal solution. And so if we want to think, will this dissolve in this type of thing, we need to consider the intermolecular forces involved in making a solution. So think about where we're starting off. First off, we have just solvent on one side and then solute on the other side. And so I'll draw my little solvents as these little kind of circles, all kind of interconnected. And then I'll draw my little solutes as these little kind of stars, right? And remember, we just learned that all of these things have intermolecular forces that are keeping them together. So these are on the left, we have solvent-solvent interactions, right? There's things that are keeping these little circles from separating from one another. There's intermolecular forces there. And then on the right side, we have solute-solute intermolecular forces, right? There's intermolecular forces keeping these together. And so if we want to mix these two things, the first thing we have to do in theory is break all of these intermolecular forces. So we have to break the intermolecular forces of the solvent-solvent. So we'll call this the delta H of solvent. It takes energy to do this, right? We need to break IMFs, the intermolecular forces. And so this is an endothermic process. This is going to take energy. And then same thing on the right side. We need to break these intermolecular forces. So we'll call this the delta H of the solute. And again, same thing, it's going to be endothermic, right? And so we're gonna put energy into our stuff to break up these intermolecular forces. And then what we get out at the end is our solution, right? So we have this little star dissolved in our circles. And now we have new intermolecular forces between our solute and our solvent. And so we'll call this the delta H of the mixture, right? So this will be kind of the solvent-solute interactions. And since we're forming intermolecular forces, we're kind of essentially forming a favorable process. That means that this is exothermic. So you can see we have to put energy in to break these intermolecular forces, and then we get energy out when these new intermolecular forces formed. So this is the process known as solvation. So in the process of solvation is the process where solvent molecules surround and dissolve the solute particles. And so the overall energetics of this situation will depend on the exact numbers of these intermolecular forces. So let's start off with some scenarios. So if the delta H of the solvent, so the solvent-solvent intermolecular forces, and the delta H of the solute, so the solute-solute intermolecular forces, is less than that of the delta H of the mixture, we will have mixing forming. And so here we'll have an overall delta H of a negative number, right? So this should, technically this should be absolute values, right? So our new intermolecular forces are stronger than our previous intermolecular forces. And so that's going to be favorable for mixing, and we'll have a exothermic process here with a negative delta H. Next scenario, what happens if these two are equal, if our intermolecular forces are exactly the same? Well, here we're still going to have mixing. And why are we still going to have mixing? Even though the delta H here is 0, we cause an increase in the dispersion of matter. So we cause an increase in entropy, and so this process still occurs. And then finally, we have a situation where our intermolecular forces between the solute-solute and solvent-solvent are greater than that of our mixture. And so here you might predict that it won't mix because we'll have a positive delta H, so we'll have an endothermic reaction. However, this isn't always true. So this may or may not mix because we're still causing an increase of entropy. So it really depends not on the sign of this delta H, but the magnitude. If this is very, very large, then it's not going to mix. If this is pretty small, then it probably will mix. So this kind of idea of these intermolecular forces and the solute, solute, solvent, solvent compared to the mixture intermolecular forces explains the whole saying of like dissolves like. So here's just kind of a picture of this. So this is all showing favorable interactions or things that would cause a solution to mix. So here we're mixing heptane and pentane. And so you can see they're both CH molecules. The CH bond is very nonpolar. And so this just has London dispersion forces. And so these will mix. In this next example, we've got acetone and chloroform. Here, both of these have a dipole. And so they're very similar and they'll mix because the intermolecular forces of the mixture are very favorable. Here, these two, both of these have hydrogen bonding, so that's very favorable, and they'll mix. And then here we have a salt being dissolved in a polar solvent, so we can form these ion dipole mixtures. And again, that's very favorable, so it will mix.